So after that extended introduction in the last video, when we went back to 801 and talked about a mass going up and down on a spring, we're now ready to do LC circuits. And what we're going to see is that the math of an LC circuit is identical to the 801 math that we reviewed. It's identical. We'll get there. So let me introduce then the LC circuit. And if I just said, here's a circuit, it has an L and a C, and just closed it with an L and a C in a loop, nothing would ever happen because there'd be no battery starting anything off. So we need to actually start this circuit off with a little trick, which I'm going to describe first. So we're going to start with this circuit. It has an L and a C and a battery and a resistor and a switch right here. And I'm going to start things off with this switch connecting this lower terminal to the top terminal. And in a second, I'm going to flip the switch so it connects from the lower terminal to this terminal on the side here. But right now, the switch is connected as shown. So at this second, this L is completely irrelevant. And at this second, I have a circuit that we've analyzed before. I've got a battery driving a charge onto a capacitor. And when there's a current flowing, that current is flowing through a resistor here, R. So what happens? Well, we know what happens. This battery loads this capacitor up with some positive charge on this plate, a negative charge on this plate. And so there's a charge Q here, which is positive, and there's a charge, and then there's a negative charge minus Q on the other plate. And very good. We wait for a good many time constants until the capacitor is fully loaded. This Q then is going to be the maximum possible Q that this battery can put onto this capacitor, and we learned how to calculate that several videos ago. And then after we have this fully loaded capacitor, we then come along and we flip the switch. So I then come along, and instead of having the switch connected as I have started with, as I did at the start, I flip the switch so that now the switch is connected like this. And now all of a sudden I have a fully loaded capacitor in a circuit with an inductor. And this is the LC circuit that I want to analyze. So I want you to start thinking about what's going to happen now. I've got a fully loaded capacitor. It's got all this charge with all this plus Q here, all the minus Q there. So remember, this Q is positive, and there is minus Q on the other plate. What's going to happen? While you're thinking about what's going to happen, I'm going to erase the top half of the circuit, which now is completely irrelevant. The only reason I had this top part of the circuit was to load the capacitor up to start things off, so that something interesting will happen. After we've done that, we can forget about it. So here now is my LC circuit. And in fact, I don't even want to think about the switch anymore. We're not going to use this switch. So I'm just going to draw this circuit with the switch in the position that it was after I flipped it, connecting L to C like this. And here is my LC circuit that we're going to spend the rest of this video analyzing, prepared in the way that I wanted to prepare it, with a nice, healthy, positive charge on the capacitor. So now what's going to happen? OK, you've been thinking about it. So what's going to happen? Well, what you should realize is I've got this big positive charge here, and now there's no longer any battery pushing that charge onto there, so this charge is going to start coming off. That charge is going to push a current, which is going to start circulating around the circuit in this direction. So I have a current I that's flowing. So this capacitor is pushing a current. But at this moment, the inductor says, hang on a second, I don't like that. You can't just change the current flowing through an inductor. The current was 0, and now you're trying to increase that current. The inductor is going to make a back EMF, and it's going to push against what you were doing. And so what that means is that this current is not going to jump up from nothing to significant instantly. It's going to rise slowly. It's going to rise over some time, which when we do this more mathematically, we'll figure out what that time is. But over some time, this current will rise, but there will be a back EMF pushing against it. Okay? So the capacitor is pushing a current this way, but the inductor is resisting with a back EMF. That current rises slowly. And why is there that back EMF? Well, the reason for the back EMF is that as this current is increasing, you're building up magnetic field energy in the inductor. So at the start, let's think about the starting point. At the starting point, I have this electric field in the capacitor. So I have all this electric field energy stored in the capacitor. And now this current is starting to flow. And as the current is starting to flow, magnetic field energy is building up in the inductor, and the electric field energy in the capacitor, well, as the current is flowing, this Q is getting less. So the electric field energy is dropping. So the electric field energy in the capacitor is dropping, dropping, dropping. The magnetic field energy in the inductor is rising, rising, rising. And after some time, again, when we do this mathematically, we'll figure out after how much time, but after some time, there won't be any charge left here anymore. And when there's no charge left here anymore, well, then there's no electric field energy anymore. So no charge, no field energy, no plus, no minus, and, well, I need to get rid of the electric field energy, which actually means I need to redraw the capacitor. So here is my now empty capacitor. All the charge has flowed out. But at this moment, there's a really very nice, healthy, robust current flowing. Current's flowing all around the circuit. So our starting configuration that I engineered was not a stable solution. Our starting configuration, I had this big, beefy, healthy plus Q here. That can't just stay that way. That's going to drive a current. As that current flows, the charge drops. Now where am I? Well, now I have a big, robust, healthy current flowing through the inductor. And as far as the inductor is concerned, if that current just keeps flowing forever, it doesn't change anymore, the inductor would be happy because the inductor resists changes to the current. But if there's a nice, robust current flowing, if that just keeps going, inductor's happy. But what's going to happen now? Well, that also, a robust current flowing forever, that's also not a solution to the equations. Because what happens is that as this current flows, it starts to build up positive charge on this side. And as this current flows, it starts to make this terminal negative. So the Q that was positive before, the Q on the left-hand plate, Q on this plate, is now negative. So as this current is flowing, if the current just kept flowing constant, the inductor would be happy, but the capacitor starts to complain. You can't just keep piling charge onto me from this side. You can't just keep making this more and more positive. No way. I'm now the capacitor. I'm going to create a voltage that pushes against you. So now, as I continue the discussion of this dynamics, now what's happening is that this current is flowing, but the current is being opposed by the capacitor, because the capacitor is now filling up with charge, and it's filling up with charge with a sign such that there's a voltage pushing against the current. So the capacitor now is opposing the inductor. The first half of the story, the inductor was opposing the capacitor. So they play in opposition against each other. And what happened in the first half of the story is we started with a lot of electric field energy here, no magnetic energy there. And as the story was told, the electric field energy here dropped to 0, and the magnetic field energy here, which I didn't actually label, the magnetic field energy here got bigger and bigger and bigger. So the magnetic field energy got bigger and bigger and bigger. But now the current is getting less, okay, because the capacitor is fighting back. So now the current is getting less. That means the magnetic field energy is decreasing. And now charge is building up on the capacitor again, although with opposite sign as before, with the positive on this side, the negative on this side. So the electric field now in the capacitor is pointing this way. And now let's wait some more time. The current is getting less and less and less and less. The charge is building up and up and up and up. And there will come a time, we're going to have to figure out how long it takes, but there will come a time when the current has been beaten all the way down to 0. And once the current is beaten down to 0, then there's no magnetic field energy here. There's no magnetic field energy. I have an empty inductor. And I'm almost back to where I started, but not exactly, because I started with a positive Q here, and now I have a negative Q. So I'm back to a situation where I have all electric field energy, no magnetic field energy. I have a full capacitor. I have an empty inductor, just like at the beginning. But the sign of the charge in the capacitor is opposite to how I started. The sign of the field in the capacitor is opposite to how I started. So now what happens next is that we have the same story again, but backwards. So now if I start here, I say, look at this. I have this big positive charge on this side. That's going to start to drive a current. I'm going to start to drive a current this way. As I start to drive a current this way, the inductor objects and says, you can't just increase the current. The inductor creates a back EMF, which fights this way. The inductor is fighting against the capacitor. That means the current grows slowly over some time that we have to calculate. The magnetic field energy is increasing. The electric energy is decreasing. The charge is getting less. And after some period of time that we have to calculate, no charge left, empty capacitor. Empty capacitor, no charge left, no electric energy, and nice, healthy, robust current flowing through here, lots of magnetic energy in the inductor. Is that stable? No. Is it the same as where we were before? It's almost where we were after the first chapter in the story. We finished 3 chapters of this story now. We're almost same spot we were after 1 chapter, but after the first chapter, the current was flowing this way, and now the current is flowing that way. So it's similar but not the same. It's similar, but the current's going in the opposite direction. Lots of magnetic energy, no electric energy, but the current keeps flowing, and as the current keeps flowing, my goodness, it starts to build up a positive charge here and a negative charge there. Q is becoming positive again. The electric energy is growing, and this capacitor fights against the current, starts to degrade, reduce the current. And as the current reduces, the magnetic energy gets less. As the current is piling up charge on the capacitor, the electric energy gets more. At the end of the 4th chapter of the story, as we get ready to begin the 5th chapter of the story, we have this situation with a nice fully loaded capacitor. Q is positive on this side. The electric field is pointing in the same direction as at the very beginning. And now we really are back to the start. This is where we started, and now the story will repeat. So it's a story in 4 chapters, and it will now repeat over and over and over again as the energy sloshes back and forth from being electric to magnetic, to electric to magnetic, to electric to magnetic. So as you can see, you should start to sort of feel in your bones, there's an analogy between the mass on the spring from last video and this story that I've told qualitatively.